It's really a great pleasure to be here. And indeed, I feel very distinguished to be welcome by all of you. And I would like to start by by thanking, first of all, Masha. How many decades ago have we met for the first time in many interesting places? To Masha, to Jakob, to Yevgenia, and everyone who made it possible. It is really very important for me to be here. And I enjoy the time for the 2 days that I'm here already. And I have 2.5 more weeks, and I hope I will enjoy it as much. And I hope you will enjoy some of the things that I'm going to tell you. So what you already mentioned, in some sense, as a research mathematician, it's a bit like you're traveling salesman. You tour the world and you try to advertise some interesting mathematics. And I have a sequence of classes, of presentations for you. The first on slides, and then the rest more interactive. And one of the features of holomorphic dynamics, it is a field with very enthusiastic and active people. And I'm trying to spread some of the fun and the beauty of the subject to all of you here. And that means I hope you will ask questions. It's not that I'm trying to talk at you and, well, get rid of all the interesting things. I want to, over the time here, interact with you, hear your questions, and see that we form some interaction. And you see, university students are already on the title. And this is one of the key topics. I want to connect various topics. One thing is mathematics. Most of the theorems we learn have been made by very old people 200, 300 years ago. And nothing is new in mathematics. Or so you think. And then, well, how old do I have to get until perhaps in some remote corner of mathematics can I prove a little lemma? How you have to get beards and whatever, get very old. And then it's something very, very small that nobody else can understand. So, no, the world is different. And this is what I'm trying to present to you. And even high school students have contributed something interesting. And that's the idea of what I want to present. So I will ask you at some point, I want to meet the level of background, so I have to know where you stand and what you know. We'll talk about polynomials and the roots. For us, polynomials are in one variable, so they have some degree d, and that means, well, we get there. So, and then you want to find the roots of those polynomials for a zillion important reasons. So this is one of the most important tasks in theoretical and applied mathematics. There are some classical questions of a few hundred years ago, and some modern answers of just a few years ago, of people your age approximately. So, and then there are high school students who produced an algorithm that beats even the professionals. And that is possible too. So, and as I said, the key message is students can make a difference in relevant research problems of today. So, polynomial, what's a polynomial? Most of the time people think of a polynomial as something written in coefficients. There's a constant term, then there's a linear term, and so on, up to some higher degrees. And this is something, thank you so much. Remind me, I want to advertise this. I want to advertise a lot of things here, but this is one of them. So, you all know what a polynomial is? Okay. So, and then you're looking for roots, numbers alpha, so that P of alpha is 0. If you found such a root, you can factor out by what's called long division. The polynomial has a linear factor x minus alpha times a remaining polynomial of degree 1 lower. Right? You've seen that? And then you can continue for this. So in the end, the polynomial, if you keep finding solutions, you want to split it in linear factors. That's not always possible if you have x squared plus 1, famous example. then there are no linear factors over the reals. And so people had to invent numbers. They call them imaginary numbers. You could also call them invented numbers. But all numbers have eventually been invented at some point. So, here, I think it's an old friend of all of us, I call it the fundamental theory for algebra. Many people call it of algebra, but it's something that analysis proves for algebra. They need it, but they can't prove it. Every polynomial of degree d completely factors into d linear factors over the complex numbers. It always looks like this. And the task is, given a polynomial presented, for example, in this form, how do you find all the roots? So why should we care? Is it just a funny little question that some whatever, a remote corner? Well, I could make the experiment. Everyone probably has a different answer why it's important. I can just name a few. All of algebra, for instance, builds on this. So you have to, you have to know the roots exist, and often you need to find them and work with them in theoretical mathematics. All the way to engineering. Whenever you want to solve any numerical equation in engineering, a lunar lander landing on the surface of the moon, 2 satellites meeting, or whatever, you have to, something like a robot hitting a target. You always have to match a condition. And the condition is usually described by an analytic equation. And analytic equations are too complicated, so you approximate by polynomials. And here you go, in order to find solutions, you're down to finding roots of polynomials. Or in statistical physics, when you want to, whatever equidistributive measure or so, you want to find roots of polynomials. So this is one of the key fundamentals, it's not only a fundamental theorem, it's one of the fundamental tasks across mathematics from the theoretical side to the engineering side. So far, so good. In theory, here they are. And one of the key topics in this talk is, what is the difference between theory and practice? So what is the difference between theory and practice? The answer, there is no difference in theory. And you'll see exactly, this is kind of the subtitle of the whole talk. So, you start with a polynomial, say in coefficient form, and you can turn it into factorized form if you find the roots. Which of the two ways, going from the first to the second or from the second to the first, which one is easier? That's easier, you think. Are you sure? Well, let's start with degree 10. Then how many multiplications have to carry out? Just about 10 factorial or something. So in principle, in theory, it's very easy. And in practice, you don't want to do it if it costs you exponential complexity in the degree. How good can you do it? How well can you do it in the other direction? That's one of my results, trying to find out what is the complexity to do it efficiently. You would think this is such an important theorem, it must be known. Unfortunately, that's wrong. And it's embarrassing. You can call it a scandal. Such an important question. We'll come to the scandal. So let's start simple. For quadratic polynomials, there's the famous formula, which I guess you know. In Germany, this formula has the nickname, it's the midnight formula. Ever heard the nickname? So in high school, the teacher asked the students, and even if I wake you up at midnight, you have to tell me. Yeah. Usually it works easily at midnight, but not in the morning during the exam. So there's a formula. Then for degree 3, there's a nice formula also. You have a general cubic polynomial. You first have to compute the discriminant, which is a nice formula. And out of the discriminant, you find This is one root. And the other two, once you have found one root, you factor it out, and the other two are quadratic. Easy, beautiful, nice. So let's generalize. Here is degree 4. I won't read it for you. I hope I didn't mistype. In any case, after a few simple steps, you can solve all the polynomials of degree up to 4. And what happens in degree 5? There is no formula in general, and the reason is simple, it wouldn't fit. You see, this is the largest possible that fits on the screen, so there cannot possibly be such a formula. Well, there are a few more details that have to be fit in. Ruffini, Abel, Galois. There cannot be formulas for degree 5 or higher. So it's important, most polynomials don't come voluntarily at degree 4 or less, so you need to approximate the roots. And that's our business. How do we do it? So let's resume a little bit. Classical questions. Here is Gauss. An old question. This is the German banknote that featured Gauss back in the days, at the time when we still had Deutsche Mark. Hmm? Yes? There could be a date on it, 1993. Yeah, but the more relevant date is 1855, which is when Gauss died. So, even the bills are very old. And let alone, when the bills came out, Gauss had been dead for 150 years also. So, this is not exactly recent mathematics. And Ruffini Abel is also 200 years old. So, there is the old method in order to find the methods. Newton, you all know Newton's method? Or so you think, yes. Well, Newton, when did he live? 17th century or so. He stole it from Cardano, who stole it from the ancient Greeks, who stole it from the Babylonians. And so this is really old. Apparently the Babylonians, so a few thousand years ago, could find root 2 up to 15 decimal digits, which is easy if you know Newton's method, and impossible otherwise. Hmm? Now, who is older, Egypt or Babylonians? I don't know. They might have stolen it from each other. Maybe some Indians or Chinese or what have you. In any case, the point is clear. For something as old as this, one should know something about it. And then there is a beautiful method by Weierstrass, which we'll talk about these days, which is somehow the current highlight. So I've shown a picture of Weierstrass also. And my point is, the recent things, they're all dead. I want to talk to living people and living mathematics. And so not mathematics here, this is the kind of mathematics done by dead people. I want to come to the difference, live people. You will see live people, and they still live and still do mathematics. So, and then there's the famous Ehrlich-Abert method. I'll get to all of this. And now here comes again theory and practice. There is Victor Pan in New York, about 80 years old or a bit more. He's kind of the guru of all theoretical methods. He has an algorithm for finding all the roots that is best possible, and he can prove it in theory. Unfortunately, it does not work. So, and then there is the other guru, Dario Bini, is in Pisa. Well, late 60s, I would say. They're both friends, and we work and talk quite a bit. He has the best possible implementation. If you have a polynomial, you want to find the roots, they have the implementation called MP-solve, and it finds you the roots. This is kind of the gold standard for the solutions. This is the best possible in practice. Little problem, nobody understands why it works. Let me repeat that. It's the gold standard method, and nobody understands why it works. I believe it doesn't. We get there also. So, can you combine theory and practice? Do you understand the scandal? Thousands of years, and the big results of a few hundred years old. It's an important result, and nobody knows how to do it. There are methods without, nobody knows why, or other methods which you understand that don't work. You could say it's a scandal, or you could say it's an opportunity. It's a great chance to contribute to mathematics. It's part of my chance. It's part of what I do for a living. That makes me a traveling salesperson. At least one of the topics. So, Newton's method. I didn't have as many O's on the keyboard as I would want to write old. So, what do you do? Probably you know this. Let me draw a better picture. So there is some graph or other. Well, it should be a graph, like so, and then when you start somewhere, is this a root? Know the value. If this is p of x, the value is non-zero. Then you draw the tangent, see where the tangent intersects, evaluate the polynomial there, still not zero. You draw another tangent and so on. You know this? So it gives you a picture a bit like this, in good cases. In other cases, if you start at this point, maybe near the root, so then the tangent, it goes up here, and then what I want to draw here, if you're near the inflection point, then the tangent is almost horizontal, and you travel quite some distance, and you find some other root, if at all. So, I think it's a great method. And so, half of my research agenda in this field is to show that Newton's method is very good. And the other half is to show that the other methods are very bad. Kind of. We'll get to this also. So, why is it good? Locally, it converges very fast. So, if you are near a root, near a simple root, then in every step, the number of valid digits doubles from step to step. So, in principle, if the Babylonians found 16 valid digits, just 4 iterations. 1 digit, then 2, then 4, then 8, maybe 5. A few iteration steps. So, if you know the method and can compute precisely enough, then this works once you're near enough. It's very easy to implement. You can compute Newton is x minus p of x divided over p prime of x. If p is a polynomial, then we have a rational map, and you want to iterate the rational map. So it's very easy to implement. You should write a program on the computer yourself. Another thing is it's very robust, and you shouldn't underappreciate. Often when you make a computation and you have a round of error at the beginning, somewhere in the 10th digit, then as you continue working, the round of errors will get ever bigger. No, here they get ever smaller. So you don't have to compute very precisely, and what errors you get, it's getting ever better as you iterate. Not every algorithm is so nice. And in modern days, parallel computing is always an important thing to do. You can do this very easily. Okay, so these are the good sides. There are some problems. Problem for us means challenge and work to do. What is the global convergence and dynamics are not, or they used to be not so good understood. So numerical analysts, if you look at textbooks, they will often say, Newton's method, don't use it. It's well known, it's chaotic. So chaotic, unpredictable, don't use that, we have better methods. So what are the better methods? Talk to the numerical analysts. But if the experts all agree, why should we work on Newton's method? And how can students make progress centuries later for such an old topic? So, chaos is not a problem. We love chaos. So, originally my work is on chaos. What have I shown here? This is the complex plane. This method works just as well over the complex numbers. You all know complex numbers. So they live in the complex plane, good. Tomorrow I offer some background for the complex analysis that's required, but just dividing complex numbers isn't much of a problem, okay? Please ask questions if I should explain. Also online, hey folks online, if there are people, ask questions. I wanted it. Yeah, okay, that was the first question. So we should celebrate. Yes, people should ask questions. So what have I shown? Here is the complex plane. And you should see thick dots and small crosses. The thick dots are the roots of the polynomial. 1, 2, 3, 4, 5, 6, 7. So this is the degree 7 polynomial. Did I write this somewhere? No. So this is one root, and all the purple points converge to this root. All the red points converge to this root, but do you see some red spots over here? The yellow ones go there. Here green is a bit more interesting. And of course you see quite some green all over the place. So there was Cayley, 1876. He has a theorem saying, suppose we have a polynomial of degree 2. Here are the roots. Then you draw the bisecting line between those. And everybody on this side will converge to this root, and everybody on the other side converge to the other root. It's very simple. Try it out for yourself. So that's 1876 Cayley, and he says an analogous result for degree 3 polynomials I will publish soon. We're still waiting. And his problem, he didn't see computers. To have a picture here, this is degree 1 special degree 3 polynomial. So I don't think Cayley could have anticipated that.
This is degree 2, right?
In degree 2. In degree 2, it's very simple, and only in degree 2.
And what about the points on the line?
They stay on the line. So this is who of you knows the Riemann sphere? You do? So here's the Riemann sphere. Some people call it a complex projective line, or C hat, or C bar, whatever you call it. And we have the map Z maps to Z squared. Here's the point at infinity, here's the point at 0. And when you keep squaring, here's the unit circle. Everything at value less than 1, and the squaring goes to the origin quickly. Everything at value bigger than 1 goes to infinity. And the value at 1 is invariant, with interesting dynamics, chaotic dynamics. So that is the same dynamics in suitable coordinate systems. It's not obvious, but it's true anyway. So Newton's method for quadratic polynomial is as simple as complex squaring. So you see, it's a complicated but very beautiful and very interesting thing. And this is the kind of mathematics that has become possible only once you had computers. And then you see what happens. Without, you're like Cayley, and it's hard to guess. Okay, you could ask, so this is over the complex. What if you talk about real polynomials? Who needs complex numbers? They are not real anyway. So here I've drawn a polynomial. Let me try to sketch the real graph. It's a bit like this. How many roots are here? Hard to draw, they're very nearby. I don't want the exact number. Let's look at this picture again. Here there are, well, blue, yellow, light blue, and purple. Must be 4 roots. If you just look on the real line, you will not see it. It looks complicated. But if you're looking a bit from the outside, you see very easily it's 4. Right? So this is one of my favorite sayings. Real mathematics is difficult. Complex mathematics is beautiful. You see that in the real it's very difficult. And you have the beauty of all complex. And then it's much easier to find the roots. Okay, so far so good. Now let's go to the interesting things. There are some bad starting points. If you're unlucky, and if you hit a point where the tangent is horizontal, then you jump to infinity and stay there. So that means it's the pole of the rational map. And you go off to infinity. And then, too bad. But there are only finitely many poles, and maybe that's not too bad. If you evaluate a polynomial at infinity, to me the values are very large. So infinity, no, infinity is not a root. P of infinity is infinity if you wish. So here the smart people, if they don't find the answer, they change the problem, and then it works. Old trick. But it may even happen, well, you probably don't only find them many poles. You will probably not hit them exactly. But you can get near the poles, and then you jump off. In fact, this is what you see here. Let me go all the way back. This is the Riemann sphere, the same picture I've just shown you. And here is the point at infinity. So you see all the basins seem to touch there. At infinity. And when you add infinity, well, if you directly add infinity, you're lost. But you can get close to infinity, and then you see the iterations. It will take a long time until you come back and do something unpredictable.
It's also not stable. Small variation, and you get different bases.
Right. In this case, it's good. If infinity were stable, then you would drift to infinity, but you want to get away from infinity. So this is the same dynamics out at infinity. But you can now you see here, for instance, that's the pole. So near the pole, in one step you're near infinity. So you see the behavior from near the pole. So this is kind of a telescope at a finite point that looks all the way over to infinity.
And what are the crosses?
Very good question. So the crosses are roots of the second derivative. So there should be 5 of them. 1, 2, 3, 4, 5. And why do I draw them? So now this is mathematics. I will explain this at some later point. One, the fundamental theorem is that all these basins are simply connected and go to infinity. They all meet at infinity. And they go to infinity like this one that can go in one direction, or this one goes to infinity in 2 directions. And green 1, 2 barely has 3 directions. We call them channels. In order, you see that? It's a pretty narrow channel, but still.
Do we have many poles on this image, right?
Well, the poles are the roots of P prime. There must be 6 poles. They're not so interesting. 1, 2, 3, 4, 5, and I guess there's one heart here, 6 over there.
Other blocks are kind of pre-images of that.
Everybody has pre-images.
So number of channels
Exactly. So if everybody gets one channel for free, and if you want to have an extra channel, you must have in this component an extra root of the second derivative. It's an inflection point. So there's one inflection point and there are two. Here there are two inflection points, and so you get three. And you see this inflection point is very close to the boundary, so the channel is narrow. If you move a little bit the roots, maybe it disappears and then the channel closes off. So that's one of our first theorems in the whole subject. Welcome. So can we ask part of the audience, I have a very active audience here, which is good, tell you in a few words, oh, you're the photographer. Okay, so this, yeah, okay. So then I was told to ignore you. Sorry, this is, yeah, okay. In a friendly way. Yeah. Okay, so.
Do both have preimage on the left?
Yes? This guy, for instance, will eventually go here, 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 and then it's a pole. In fact, preimages, iterated preimages of poles are dense on the boundary. So whenever you have a boundary, the dynamics on the boundary is chaotic. I'll have to define chaos at some point. But then everything happens pretty much. Okay, so let's go back to this one. Further problems. We discussed poles or almost poles when you jump to near infinity. Here's a more interesting thing. Obviously, when you're in red, there's some red dots. As you iterate the red, you will stay in red, eventually converge to this root. All the blue points eventually go there and so on. But if you're on the boundary, like here, if you're on this boundary, you must stay on the boundary. So the boundary can never converge to any of the roots. It could be that the boundary has positive measure, which you may find surprising. And you should find it surprising, but it's a theorem. It's a theorem that there are cases when the boundary of these guys has positive measure. So with positive probability, you hit a point on the boundary and then you stay on the boundary. It's a deep theorem to prove that, and it's 20 years old perhaps. So it is really new and surprising, but true. But maybe not too dramatic, because the boundaries are not stable, it's chaotic. So when you're on the boundary, you will, with numerical round of errors, get away from the boundary and then drift to some of the roots. But the more dramatic problems. Do you see this black disk? And there are lots of black disks all over the place. Whenever you're on this black disk, you move to this black disk, to this black disk, to this black disk. And then there's a small black disk somewhere here which you don't see. This disk goes there and comes back. And you always stay in this two cycle of disks. So there is really an open set of points that jumps back and forth and never goes to any root. And that's not exotic. Here, z cubed minus 2z plus 2, the world's simplest polynomial. This is the dynamics. So, sometimes I find it interesting, but you could say for Newton's method it's bad. That's when it doesn't converge, and it does happen. So that's pretty much old news. And then, of course, if you want to understand how to find the roots, where are they? How can you iterate? You want to understand the global dynamics. If you have degree d and d is 100 or 1,000,000, you want to find 1,000,000 different roots. And globally, it looks very complicated. How can you make sure that you find all the roots? After all, the map is chaotic. And then all the roots, you know the word deflation? That's long division. If you have a polynomial of degree 10 and you find two roots, you can divide them out, and what's left is degree 8. That's deflation. So in principle, if you have enough roots, you can factor them out and start again. In theory. And in practice, the new polynomial that you get out has the roots, you make some errors, the roots are slightly off. And when you do it again, the roots are slightly more off. And this is unstable. So if you make it a few steps, then you, the new roots have nothing to do with the ones you were originally looking for. So I'm always for the ambitious things. I want to find all the roots without deflation, even for degree million and more. And then I want to control, somehow, I'm a theoretical mathematician, this is very applied. But I want to prove it works, and I want to give an algorithm, tell how long it takes. And all this is possible. So when I started, I was saying, okay, I do dynamical systems. I don't want to compete with the experts, but I want to understand what's going on. Over the years, I've learned that the experts have fast methods that they don't understand. And when I started, there was no method that we really understand. Now we are making progress. But the numerics people don't care how it works, as long when they try 10 times it works, that's enough. Good for them. But I wanted more. And I started talking to them, to the numerical experts, on the day when, so they have some website, here is our method, try it out, MP-solve the method, try it out, and here are some sample polynomials. And they have a particular sample polynomial of degree 1 million, that we're very proud that I get to this. So let me just quickly say, my high school student was beating the professionals on their sample polynomial. So what they were advertising, how well they could do it. Details are coming. So is this all? Yeah, okay. So here's the theorem. And that is, in hindsight, the first theorem ever. So all the root finding methods have local results. If you're near the root, then you convert quadratic or cubic or whatever. That you understand easily. But globally, nothing was known for no method at all. And the first result was this. John Hubbard, you'll see a picture of him earlier, was my PhD advisor. I had just finished my PhD. Scott Sutherland had also written a PhD on something similar. So you fix the degree D. And then you have to normalize the polynomial that can be large or small or somewhere else in the plane. We normalized only one normalization so that all the roots are in the unit disk. They have to be somewhere, you just normalize it somewhere. And this is, you don't lose any generality, you just have to have some bound on where the roots are. So you know the degree and you normalize it. Then there is a universal set of starting points, which you can actually write down, a finite set, so that for every root of every polynomial of this degree, one of those points will converge to the root. And this universal set, depending on the degree, has small cardinality. You want to find D roots for Newton's method, so you must start at least at D points. So you shouldn't be surprised to see a factor of D here. And then there's a fudge factor of log D squared times a very small explicit number. So it's not like D to the 100, or what did we have, D factorial earlier for this. It's just a bit more than linear in D. And that's enough to always find all the roots. And there are classical results. I'm not an expert on it, I just use it. There is if you have, what is it? A d z to the d plus something like this. Then you can give a bound. If z is too big, then this term will dominate all the others. It's an easy estimate, just this one should be bigger than all of these. Yes. In some sense, you can do it. I don't remember it. I think here z is less than, let me divide out by the first coefficient. We lose nothing by that. Then this, I think it's something like this. Yeah, which it's not very efficient, but you can do that. And here we try to do what we can do well and don't touch what we can't do well. And this is not something where we have something new to say. The other question is, precise evaluation of a polynomial also is a tricky issue, which I will not discuss. But if you have degree 1,000,000, how do you evaluate the polynomial so that the answer has anything to do with the question?
What are the 3 points for d equals 2?
Say again?
What are the 3 points for the d equals 2? You explicitly know.
Here. That is degree 50. Yeah, I think for degree 2, I think you just take 3 points on any circle around the disk, make the equidistributed, just a triangle. I mean, here it's, in this case, so the roots are here, so here's the disk around it. Then you take a larger circle. And we know that the circle is cut evenly. So if you take 3, you'll find them. You just take any circle that surrounds the disk, and on the circle you take 3 equidistributed points.
So this formula for small d, it works
Yeah, I mean, it's not very interesting for small d, but it is every degree d. Yeah, even degree 1 if you wish. I will say something in the end, you can get it even better. The cardinality in a probabilistic way. Get the same factor of d times the square of log d. Double log. And the double log, so in theory, it is proven that log d goes to infinity when d is large. But it has never been observed in practice. Try it out.
What type of probabilistically is it? By almost surely or by probability?
So you tell me the probability of success, and then I tell you the constant. So if you want to be sure that 99% success, you get a constant. And if you want, so this is 10 to the minus 2 error rate. If you want to get 10 to the square of the error, 10 to the 2 to 10 to the minus 4, you take twice the constant. It takes twice as many points independently. Okay.
Is it that like we uniformly choose this set and then calculate the probability, or?
So I want to show several things at one time. Here, one factor of log d is probably necessary. And here, for these nice cases, you need log d times, I think, log 3 or so. D log d times log 3. So probably a single log d is good enough. But it can be that you get very narrow channels. Here we have a thick channel, which is good, but can it happen that you don't have this and you only have 2 very narrow channels? It can happen. You have to construct it accordingly. And then there can be only very few narrow channels. And to find those needs the most points. In fact, for those, you have to go from log D to log D. And the probabilistic method says, for the white channels, you use few deterministic points. And then there's a theorem, if you have narrow channels, you must have several of them. And then you have a random collection of points. And so the narrow ones, of which there are many, you find by a random method. So it's a mix between deterministic and random.
Can you please repeat the construction of the first bit with asymptotics?
Repeat what?
So please, can you please repeat the construction? So what does this asymptotic say? So we take this universal set.
Yes. So the way the set, I will talk about this a bit later. This is the easier result, and usually it's sufficient. What you take is log D circles. I think 0.266 times log D circles. And on each of them, you have 4.19 D log D points. And now if you multiply those two numbers, you should get 1.11.
If I don't care about dependence on D, then is there easier way to see that something like this should be true?
What do you mean if you don't care about D?
So
If you take 100, or if you don't care about the constant,
yeah, like if I'm okay with having two D points, but I just want some finite number, some finite number that's allowed to depend on D in whatever way.
Why
I'm
should-
trying to see why the difficulty sits in this.
the beauty of this is, and if you're interested, one of these days I'll talk about how you do it. But the beauty is that you set it up in pretty much in the first step, so the log D circles that you get completely remove the log D dependence. So rather than thinking, in fact, Sutherland before, he used a single circle, and all the computations were wrong. But if you do it correctly, it is d to the 3/2 with difficult calculations. And here, this way, I can rescale away the problems, and then it's the universal problem. So that way, except for the constant, which I worked hard on, other than this, just to get the asymptotics, this is the easiest way to do it. If you just choose, like always, if you choose the right coordinates, things get simple. And pretty much what happens here. And I know, this is a more complicated proof for a much weaker result. And I don't know of either a simpler or complicated proof for a weaker result. And I haven't thought about it. You'll see this is easy enough. Okay. So this is degree 50 again. And you have 47 roots on a circle. These are the yellow ones. And then 3 colored ones. And gray, again, are domains which don't converge. So this is an interesting phenomenon where there's an open set of starting points that don't converge. So even in this case, and it may well be that some of those starting points will fall into the trap of the gray points and don't converge. Or it may be that some of them all converge. There will be many of them that converge to blue. So if I have 50 starting points that converge to roots, I want to find 50 different roots. Except if I have multiple roots of the polynomial, and then I want to find exactly those triple root here. And rather than just having 10 orbits converge to this one, if it's a simple root, I want to have a single one. So this is all guaranteed in the theorem. So here are 3 pictures Remember, the first theorem was with John Hubbard, and this is a very typical picture of my PhD advisor. And then the other two, let's go back to this. Here, this is with John Hubbard, and Scott, I don't have a picture of him. And the probabilistic is a nice event with students, Bela Bolobash. Anyone heard the name? And Malte Lackmann, you probably have not heard. This is Bela Bolobash, and this is Malte Lackmann. And so the little advertisement or not, Bela Bolobash, Malte, and myself met at the 50th. I organized the 50, International Mathematical Olympiads. You went there?
Yes.
Where?
I was online 2 times.
At the wrong place.
It was supposed to be in St. Petersburg
Yeah.
2 times, and I was 2 times online 2 times.
Okay. So I barely failed to participate, so I had to bring one to myself. One of those days, there will be one in Kiev, and I'll be happy to help. In any case, since I couldn't go, I organized one at where I was in Germany at the time. And it was the 50th IMO anniversary. So we could invite some of the most prominent living mathematicians who in their childhood had participated in IMOs. So we had Terry Tao, we had Bela Bolobash, we had Yokos, we had Lassi Lovash, we had Stas Smirnov, and I owe you the sixth name, Timothy Gowers. So the who is who of mathematics came, and here they were in the City Theater speaking. Here they are. And then Terry Tao orthographing for the students. And one of them was Bela Bolobash. He is here. And Malte was a participant. And so, congratulations on your IMO, but I'm a little skeptical about them. This is the IMO. So here you see 500 of the smartest young people in the world who do all the same thing. They must not talk to each other. They must not use books. And after 4.5 hours, there comes a jury with a marking scheme. That's ridiculous. Smart people like you guys shouldn't do something for which the jury has a marking scheme. All right, you should do something new. So, but anyway, it was a little bit, I was there, but I learned these are different worlds. Anyway, so we had, in this IMO, we had the guests of honor, and I decided, let's do some interesting things. And out came, as I said, a paper with a participant and one of the guests of honor. So that produced actual mathematics. And you know the Aders number? You know what that is? So meanwhile, this Malte, through that paper, has Aders number 2. Because the co-author is Aders number 1. So in case you don't know this, Paul Aders, one of the, there were a few mathematical gurus in the previous half century. The other one is John Conway. I'm happy to talk about John Conway. He was a friend of mine. Also, so Aders produced zillions of papers with zillions of co-authors. Aders has Aders number 0. And then all his co-authors have Aders number 1. And then the co-authors have Aders number 2. This is how you get it. And perhaps Malte is the youngest with Aders number 2, or one of the youngest. Also, yeah, right. So you have to write a paper with me and you get the thing.
I think I have 3 already.
Then you have to work with Bela. It's getting harder. Okay, so that's the IMO story. Now let's see, probably I've used much more time, which is good because you should ask questions. Yeah, I have a few more minutes. Maybe I will quickly click through the slides and hope you come back. How is that? So, one question is, Stephen Smale observed that there are problems like this. And he wanted a classification of all the polynomials where this happens. And so that's, and here, no, this is a must discuss. Here is the space of all cubic polynomials. So polynomials have cubic polynomials z minus alpha, z minus beta, z minus gamma. The leading coefficient cancels out. So you can write them like this. Choose convenient coordinates. So by the translation, we can assume, at least theoretically, that gamma is 0. Doesn't change the polynomial, just changes the coordinate system. And then by rescaling, we can assume that beta is 1. So really, the polynomials can always be written, with a few exceptions, alpha is lambda, like so. Just we've lost nothing. This is the general cubic polynomial for Newton's method. Now the question is, for which values of lambda do you have this problem that there's an attracting cycle? Or for which is the boundary of positive measure? So this is the lambda plane. Every parameter lambda is a different cubic polynomial. And then you can ask, so for when the colors, somebody will ask me what the color means, and I will answer next time. I'm running out of time. But the color black means it's a problematic one. So here is a little blow up, and if you look like this, this is the blow up of this. And it's a further blow up. Do you guys recognize this object? The Mandelbrot set. Here's the actual Mandelbrot set. Who of you has not heard of the Mandelbrot set? Who has never seen this picture? Everyone has. So now, how come that all, and that's a theorem. I think it's the next slide. No, it's not here. It's a theorem that all the cubic polynomials for which there is an attracting problem, so for which an open set of points doesn't converge, or for which the Julia set, the boundary, has positive area, they're organized exactly in countably many little homeomorphic copies of the Mandelbrot set. Each of them is homeomorphic, up to the finest details. And if you have seen pictures of the Mandelbrot set, there are lots of little Mandelbrot sets in, you will find them all here at the exact same places. And that's a theorem.
What is the fundamental group of the Mandelbrot set?
I'm not sure. Very good question. It's connected. Very good question. I used to say, if you prove that, and you're under the age of 40, you get a Fields medal. That may no longer be true, because presumably at the next International Congress of Mathematicians next summer, the proof will be announced by a former student of mine, who is a bit older than 40, unfortunately. So, a weak statement is the Mandelbrot set path connected? If it's not path connected, it's connected. But is it path connected? That is, at this point, I think, an open question. And if it's not path connected, what is the meaning of simply connected?
Is it open, closed?
It's closed, it's compact. But there are all the interesting sets that are closed and compact, which are connected but not path connected. Probably not so, but that's a deep question. And several people got Fields medals for partial results, such as Yacoz and McMullen. So it's a deep question, and it will soon be resolved. And I'm very proud that one of my PhD students is one of the 3 key actors. Come next summer to the ICF. Okay, so this is certainly a topic I want to explain. And you should be surprised, and you should. Hubbard keeps saying when he discovered this on the computer, he fell off his chair. How come? There is a paper by Fields medalist Kurt McMullen with the title, The Mandelbrot Set is Universal. And this is just a special case of why this is so. In fact, you take, there are all these colored sets, you take any boundary point you like. You take any small neighborhood of it. And in it you will find countably many little Mandelbrot sets, all homomorphic, with the same problem. I'd like to explain to you why this is so. And why this is not a miracle, but there is a natural, very natural theory behind it. So then, I'm not sure how precise we have to be here. I'm out of time, so let me click through these and then conclude. So this is kind of a zoo of different ones. Try to understand why this is, what are the possible shapes you get to see? And that gives me the opportunity to talk about another Fields medalist whom I haven't mentioned, William Thurston, who has a theory, big machinery, and using Thurston's theory, a former student of mine, Zhenya Mikulic, has classified all the possibilities, including all the cases of when you get attracting cycles in the problems of all degrees. So, this is the possible candidate for the seminar talk next week. But I have to skip this, and these are the details. And so here's a theorem which we can also discuss. I showed you where you have to start. And the theorem tells you how long it takes, how often you have to iterate to find this all. So, but let me, here, so this is Robin, very much alive. He was 18 a few years ago, like all of us. He's a bit older. At the time he was in high school. And this is the sample polynomials for the professionals, MPSolve, that they advertised on their system, and Robin was worked on it. So he managed for degree 1,000,000, found this all in 5 weeks computer time. And then with a new idea, better compiler system, whatever, it was 3 hours. We were so proud. And then we improved the algorithms, and it was 10 minutes. And then, by that time, we talked to the producers of MPSolve, the experts. And I, shy, won't believe it, but I was shy, talking to the experts in numerical analysis. Hey, we have tried a little bit, and they invited us to Pisa, Robin and I and another student. They got to degree 2 to the 24, which is 4 million. And on their university computers, they could do it in 5 months. And then comes Robin in 9,000 seconds on his old laptop. So this is where a high school student beats the professionals on their polynomials in the 21st century. So that's something. What did he do? And you see it's an important problem, and you can make progress. So let me still conclude. We've gone up to degree 10 to the 9, meanwhile, with another student. And then friends of mine in Paris, now they're at 10 to the 12. Unfortunately, that's not a high school student, but it's, well, still, we challenge the people, and then they challenge us back. Let's not get into this. Here's the table. 2 to the 30 is 1,000,000,000, 10 to the 9. And in about 93 hours, degree 1,000,000,000. And of course, you found, what else do you see? 179 different attracting cycles. You have to find and you have to get rid of somehow. So, and you see the complexity, number of iterations, scaled by d times log d to power 1.1. Very nice efficiency. So that is progress. Let's skip all that. But still one direction. So the numerical analysis people, they still don't like Newton. They use a method, remember the picture of Weierstrass, long dead, gravestone, 1891. This is a method for a degree d polynomial that wants to find all the d roots at the same time. So you iterate vectors of d complex numbers, and ideally they converge to a vector of the roots. And so these methods have passed the test of time since 1891, so they've always worked. So that's what you do. If there were a problem, it would have long been found. Or so they thought. And then the surprise came just a few years ago. It also doesn't work. There are similar open sets of polynomials with the same problem. And in this case, pretty much the simplest case, has this form. And that was not a random discovery. There was at the time a PhD student of mine in Marseille, Bernhard Reinke. And he said, hey, that's a problem that's coming from numerical analysis. My advisor views this as a dynamical system. I want to look at it as something algebraic. And then he was setting up computer algebra. So walking through all the domains of mathematics, set this as a computer algebra problem. And I can talk about it in a later talk. Discovered that it has the same problem. So this is bad and all nearby, but this is now 5 years old. And so, have you seen the flyer? There are 3 pictures. It's a bit, for graphical reasons, cut off. This is the Mandelbrot set, the classical one. This is a detail from cubic Newton's method. And the 3rd picture is the same thing for Weierstrass, the polynomials for which Weierstrass doesn't work. Unfortunately, nobody understands why. So I can, if somebody asks me a question, I'll show it on the computer afterwards. We also get a Mandelbrot set, or something that looks like a Mandelbrot set. But the theory that we have does not work. So we need a young, enthusiastic person who is interested in this question and finds a wholly new conceptual reason why, of all things, there is a Mandelbrot set or something similar to it. Something we don't understand. So it's not just mathematics of 500 or 5,000 years ago, or 20 or even 5 years ago. Part of my talk is about mathematics in 5 or 10 years and this new generation. Ehrlich Arbeit, the other method you can talk in here, is this not generally convergent? Probably not, but it needs active people to work on this. It's more difficult. We can talk about this also. So that's the moral of all my stories. Mathematical results were not all done in the 19th century. But a lot of questions are open to this day for young active people. And the moral of the story is, everyone agreed this was impossible. But then there came a crazy guy, he didn't know that, and then he did it. That's how to make progress. So, last slide, I guess. What I have, I thought there were 5 or 6. I have a bunch of topics. Tomorrow, if need be, we can discuss what results in complex analysis are necessary. And here I should advertise. I've been writing a book, still in the writing, on why there is the other embarrassing thing. We don't have a good book on the Mandelbrot yet. And it should be written, and this will be it, but it has to be finished. Yeah, and it has an appendix on what little mathematics is required. That's in the appendix, and I'm happy to discuss that tomorrow. So then I'll talk to some introduction to complex dynamics, the Fatou set, the Julia set, the Mandelbrot set. And why are there the little Mandelbrot set all over the place? So why are they universal? We discussed that. So, sorry I've overused the time, but once you get energy, and I was sick when I started, now I'm perfectly fine. Thank you for your attention and your questions.